Welcome back to Physics Roadshow, the second, where the fun never ends and neither does the physics. This time, instead of Josh Underdown, he's gone from his alcoholic habits. And this time we have...
Hi.
This week we're talking about argon dating. Argon is in ancient rocks because potassium has decayed over a long space of time.
We were going to start with the joke, but all the good ones are gone. So potassium, just like all other elements, decays by random processes over time, and the half-life is the time it takes to get down to half its original mass. As a sort of experimental model of this, we can use dice. If we assume that every time we roll a 6, it's decayed, then we could work out a half-life for the dice by removing it every time we get a 6. This time we will be measuring it in rolls rather than years. So 2 rolls. 3 rolls, and we are now down to pretty much half of our original sample in 3 rolls. So that's pretty much that's more or less what we'd expect, because there were about 7 dice, and it's about 1 in 6 chance of each decaying. Potassium decays in 2 different ways. The first one is electron capture, where the nucleus captures an electron from the inner shell and spits out an electron neutrino. Like so, if we assume that Sanford is our potassium nucleus.
Yep.
Ta-da! And then he spits out the electron neutrino.
Ugh.
The other way the potassium can decay, again, here modelled by Sanford as our potassium, is by beta minus decay, where the nucleus simply decays, throws off a beta minus particle in one direction, and an electron antineutrino in any other direction. So the half-life of a potassium nucleus is 1,250 million years, which is slightly more than the 3 dice rolls I just did down there. In fact, it's so long that if you draw a massive timeline of it, which stretches quite a long distance, then you suddenly find that the entire lifespan of the human species is about the width of your little finger.
It's also how long Fleming takes to do any mass equation. Beta minus decay is 8 times more likely than electron capture.
And that means that for every argon atom, there will have been 9 potassium atoms in your original sample. So, if our current amount of potassium is N, and our original amount of potassium, made by adding our current amount of potassium to 9 times the amount of argon we've got, is N0, then we can use the N equals N0 times E to the minus lambda T, and find out how old our sample is.
I'm just doing an awkward pause here.
We are the spooky men. We build enormous structures, sing at lower frequencies.
Just awkward.